On our second installment of Fun Physics, we are going over Chapter 17, problem number 36, which asks about the treatment for a stroke. It tells us, one suggested treatment for a person who has suffered a stroke is immersion in an ice bath at 0 degrees Celsius to lower body temperature, which prevents damage to the brain. In one set of tests, patients were cooled until their internal temperature reached 32 degrees Celsius. To treat a 70 kilogram patient, what is the minimum amount of ice at 0 degrees Celsius you would need in the bath so that its temperature remains at 0 degrees Celsius? So, from there we get the mass of the patient, the initial temperature, final temperature, and then the instructions go on to tell us that the specific heat of a human body is 3,480 joules over kilogram degrees Celsius, and then once again tells us our 37 degrees represents the normal body temperature. So from here we are going to use our handy dandy Q equals mc delta T equation. Our M being the mass of the patient, the C being the specific heat of the human body or the patient, and then our change in time, which is derived using the two temperatures that we have. So when you multiply all of these guys when they're in the equation, we find that Q, or the amount of heat needed, is 1,218 kilojoules. So this is the answer to part A. So after that, it asks us, well, if the man is in an ice bath, how much ice are we going to need in order to counteract this heat that is being given off by his body? So the question in part B gives us the latent heat of fusion of water, or L sub F, which is 334 kilojoules over kilograms. And we know that the heat received by water at 0 degrees is going to be represented by the equation Q equals the mass, and that's going to be the mass of the ice, times the latent heat of fusion for the water. So because heat lost by the body is heat gained by the ice in this situation, the Q right here is going to be equivalent to the absolute value of the Q that we found in part A. So our equation is going to be solvable because now we just have one unknown, which is the mass of the ice. So taking our equation and rearranging it, we find that our mass of ice is going to be determined using this formula. We're just rearranging to separate the mass of ice and latent heat of fusion. So then just going through the calculation using our numbers. Latent heat of fusion we find that the amount of ice, or the mass of ice that we would need in order to cool the patient, is going to be 3.65 kilograms. And there we have our part B.